Good morning. Uh, I'm going to be starting an AI course. Um, we're going to go from a single neuron all the way to building our own language model that can see, uh, listen. You can write text to it, language model, something like ChatGPT, and then it can generate images. We'll go there, it'll take a while. But today we were going to start with the basics of AI. Uh, what we're going to learn today is the neuron and backpropagation. Let me show you what a neuron is. And then once we're done with the theoretical basis for this, we will write code for the same. Let's say you have an input x. This is a number. And you pass it to a neuron. And for now, think of neuron as a mathematical function. It takes an input, produces an output. We will see what a biological neuron is and how it's different in a little bit. And then let's say this neuron produces an output O. O is equal to Wx plus B. This is our current definition of a neuron. It isn't 100% accurate, but we'll learn how to get better. And if you might have noticed, what's very interesting about this is that it looks a lot like y equal to mx plus c, right? It is a mathematical function which is very similar to a linear function. And so a neuron can map as of yet whatever a linear function can map, right? Let me give you an example. Um, if you have uh, particular values of x, and for them you want particular values of y, then if those values of x are, say, x equal to 1, x equal to 2, oops, and x equal to 3, then for a function y equal to 1x plus 0, you can only plot y equal to 1, y equal to 2, y equal to 3. A neuron will not be able to plot a quadratic function. Now, I will give you more intuition for the math of neuron a little bit later. Let's move further. Um, let's say now let's look at a little bit of intuition behind what a neuron does, right? Um, in AI, you're looking at patterns, and then you will learn something from those patterns. Then you look at an input and output pair, and even though you won't be explicitly told that, for example, you have values, let's say you have a pattern 1 2 2 4 4 8. This is a multiplies by 2 pattern, or 2 becomes 4, 3 becomes 6, 4 becomes 8, that pattern, right? You can plot this with y equal to 2x, but the magic of AI is in how we can uh, sort of look at these patterns, and then when you're given 5, the model will automatically predict 10 because it has learned from these three patterns that y is equal to 2x. In today's lecture, we're going to build exactly this. So, for example, you have values of x that are inputs and values of y that are, let's call this y hat. And even here, instead of calling this O, let's call this y. That's much easier, much more standard. And y hat will be the actually right answers. Y is what our neuron produces, which might not be right, but y hat is going to be ideal answers. So, for example, if you have 3, the ideal answer will be 6. If you have 4, the ideal answer would be 8. And you have 5, the ideal answer would be 10. And then when we evaluate our model, if we give it 6, it should predict correctly that the answer is 12 or whatever. For simplicity, now let's only work with the example of 3 to 6. This is going to be a y equal to 2x. That's interesting. I just had some trouble with mm, my camera recording. These are like lecture notes that I have written. You can find them on GitHub slash Avish M slash AI, um, and this would be AI1. This lecture is AI 1.1, and you go to this PDF. Okay, now this is a function for a neuron, y equal to wx plus b, like we've seen. And for an input x, if you want a neuron to predict 8, a model to predict 8, then uh, we'd like to have w equal to 2 and b equal to 0. If these two values are acquired by our neuron for w and b, then everything would be great. Just by the way, w and b are inherent properties of a neuron. Um, However, x will depend on whatever input we give it, and y would be sort of the output that this model produces, right? Uh, okay. Now, what we want to do is find, like, for example, in this case, we know that the pattern is like w should be 2, right? What we're going to look at is how, if we randomly initialize w and b at absolutely random values, how do we go from those random values to the ideal values of w and b, which again is w equal to 2 and b equal to 0. And for this, we use backpropagation. Backpropagation is gonna sort of, we'll see when it comes. Okay, now let's look. Now let's try to manually get weights and biases right. We can, let's say our model starts with w equal to some random value like 0.692675 whatever, and b equal to 0.325. With these values, when you ask our model to predict what y would be, it would be pretty off, right? Um, Given x is equal to 4 for this specific training example, y would be very off. It would not be equal to y hat at all. So if we do y hat minus y, we would be able to know how far off we are from the right answer. And that's kind of what we're doing here. So L is what we call our loss or our error, or how far we are from the right answer, is the what we predicted minus what should have been predicted, um, square. And we do square for, like, I think 2 or 3 reasons. Um, so one is it just makes everything positive. And then second one is sort of more important. If you are really, really far away from the right answer, then the loss becomes huge. But when you're pretty close, if you're like at like if you for 4 you get like 7.9, right? Y, if the y was 7.9, then 7.9 minus 8 would be minus 0.1. You square that, that would become 0.01. So for small errors, it does not penalize as much, and for bigger errors, it penalizes much more. Um, okay. Now, for for the current example, let's set y equal to 0. So let's set b equal to 0, and let's vary w so that y reaches its ideal value. In practice, we would vary w and b both, but in this case, let's just set b to 0. Okay. For x equal to 4, let's see vary w to see how x changes. When you set y equal to 4, y hat will become, y hat remains always 8. And then you try to plot the loss, that's y minus y hat. And y we know is 4w because y is wx, right? Simple math. Uh, and so when you end up solving this, you will get a plot of 16w minus 2 whole square. So if you plot the loss would be minimum for w equal to 2. That's it. We found the ideal value of w. Pretty good. Um, and so if you've done 12th grade math, you might also have the idea of, okay, if we want to minimize this L, which looks like a Y, when we have this W, which could be an X, then, or not even like, if we could just find the derivative, and if wherever the derivative is equal to 0, that would either be a maxima or a minima. Then we find the double derivative, and then where the double derivative is positive, that would be a minima, right? And therefore we can find the value of w that would minimize the loss. And if it minimizes the loss, then y and y hat are really close, which means the model is working. Great. And so the thing is, this method is actually not used because it gets kind of impossible to use in really um, complicated neural networks. But just because we have only one value here, it happens to work. Um, but yeah, you can look at this math. It's math. You can read these notes, and what you'll find is that we will eventually, after this huge bunch of math, find out. Wait a minute. Yeah, here, yeah, okay, it's here only. Setting the derivative to 0, this is dl by dw, 32w minus t, 32w minus 2 is equal to 0, w is equal to 2. Okay, so that's either a maxima or a minima. It could also be a point of inflection, I think. Just check. And then when you do a double derivative, then this now comes out to be a positive number, and therefore this is a minima. Now, obviously this method, and so not obviously, but in large neural networks, which we will see later why that does not work, it will not work. And so what we're gonna actually do is we're gonna uh, do something called gradient descent. Now this is a very conceptual thing that I need to explain. Let's say um, if you move the value, let's say w was automatically set to 17, and then our model randomly just picks out w equal to 16. So with this value of w equal to 7, let me write that down. Uh, w equal to 17 was our initial value, let's say, randomly initialized. And then x obviously is equal to 4. So wx would become 68. Give me 1 second. Sorry about that. Yeah. So wx would be 16. Okay. Now let's move w a little bit lower. And wx becomes 58. We want wx. The ideal would be wx becomes 8, right? Because x is equal to 4 and we want w to be 2. So the value went lower. So maybe let's start moving towards a lower direction. Let's move a little bit lower. It turns out we keep getting closer to 8, right? 49.2 is closer to 8 than 58 was. Okay, let's move w in the same direction. Okay, we're still moving. We're still getting closer to 8. Move closer to 8. Wait, what was our previous value? Okay, let's say we were 11.2, right? 3.2 distance away. And then we move a little bit more. And now we're 12 distance away. We move further. So we have to go back. And if you do this sort of adjustment, you can find the ideal value, right? Um, we use something that's very, very similar to what I've shown you here. It is um, so let me explain what we will actually do. Uh, what we do is we calculate the gradient, the derivative of. Um, Let me think of a good way to explain this. Actually, we will start with an example. I have plotted an absolutely random function here, and this is just the derivative of that, but we don't need that. Um, for example, we randomly started with the value of w. Let's say this is w, and this is our loss. Okay, so we want to reach this point, the optimal value of w, which minimizes our loss. Let's say we randomly started at this point. Here, the slope is going to be downwards, is going to be negative, but we don't necessarily know how the function is going to look down here. And that is basically the central sort of big problem in AI. We if we knew what this function of w versus l is, then we would directly be able to calculate the derivative as I already showed you, and everything would be perfect. But we don't know that, and so what we instead have to do is calculate like move a little bit, calculate the derivative of this, okay, and that comes out to be negative. And so if it's negative, then sort of going downwards in this same direction would lead to a lower loss. So we want to keep moving in this direction. Which direction is that? It's in the positive x direction. So if our derivative is negative, we want to move in the direction of positive x, right? So in the opposite, and if for example, if we were here, and if you're moving in this positive x direction, then your loss is increasing. So for a positive slope, you want to move in the negative x direction. This is a mathematical sort of thing to know. Additionally, you don't want to move. So if the slope is very high, then you can sort of jump and make bigger steps. If the slope is kind of small, then you might want to take smaller steps. So something that would be sort of nice would be that the size of your step can be directly proportional to the derivative. If the derivative is huge, if the slope is huge, then make a big step. But if it's like a small slope, then make a small step. And the sort of constant of proportionality in this case would be alpha. So let me directly jump to an equation that's going to be here. Yeah. So new weight is going to be the old weight, and then you move in the opposite direction of this derivative and multiply that with the what do you call it, constant, which is alpha. I will talk more about this later, but we have a little bit of maths to cover till then. Okay. Let's say we randomly started with w equal to 0.5. And this gave us a pretty bad y of 2, while y hat is 8, so therefore y should be moving towards 8. The loss, again, simple formula, becomes 36, pretty big loss. Now, we will calculate the partial derivative. And why we will calculate the partial derivative is we're going to do another lecture on backpropagation, in which we will go into this in detail. But for now, let's just know that this is a partial derivative instead of a proper full derivative. And so this is going to be partial derivative of okay. So now let me show you what the chain rule is. Yeah, here it is. Dy by dx is equal to dy by du into du by dx, right? So if you want to calculate the derivative of the loss with respect to weight, what we can do is calculate the derivative of the loss with respect to y, and then y with respect to weight, and then when you multiply those two, that would be essentially loss with respect to weight. Okay, so that's why we do dy by I don't know, delta y, whatever the symbol is. I'll just call it, okay, delta y by delta w. We do that here, and then that's going to be delta wx, because y is wx, by delta w. We assume b to be 0. We'll look at more complicated cases like, in just a very short amount of time. And in partial derivatives, we assume so if you we assume that whatever is not w, x is a constant, and so x will come out as the derivative. Perfect. Substituting x equal to 4, we find that delta y by delta w, the derivative of y with respect to w, is 4. Now, here's the chain rule, and delta L by delta W is going to be delta L by delta Y into delta Y by delta W. Delta Y by delta W is X. Now let's calculate this derivative of L with respect to Y, because we know an equation for that is going to be, you move this 2 down, and then Y minus Y hat. And then the whole thing is going to be 2y minus y hat into this X, and perfect. We have our equation here. And so when we substitute uh, the y value, we got 2, and the x value is going to be 4, then we get minus 48. Simple calculation. I think, yeah, we're right. Now, the new weight is going to be the old weight minus a constant into delta L by delta W. In practice, we have found that alpha being very small is helpful. And that's sort of because, like you don't want to jump from here all the way here and then you're jumping here and here. Like, it's much better to sort of move slowly along this curve and find this place. Because very often what you might instead do is like find local minima. See, for example, there are two minimas here, right? And you might find this minima if you move from here instead. And so sometimes running the same thing multiple times will get you a better result because there are so many minimas in much bigger neural networks. We will discuss optimization and the sort of um, like multiple minima problem much later, and we're going to look at ways to find optimum solutions, residual connections, um, and all that a little later. So here we put alpha equal to 0.01, pretty small. And so W weight new is old weight into 0.01 into minus 48, which we just calculated. And the new value is going to be 0.98, which is a jump. It's moving closer to 2. That's a good idea. And what I did now is I repeated the same thing, the simple equation 20 times. And what you see is W starts moving slowly and slowly towards its ideal value of 2. Y also starts moving towards the ideal value of 8. L, well, it's not actually 0 here. It got truncated because the decimal points go much farther. And the loss with respect to the weight also is reducing, which is something we would like. Interestingly, we, like I told you, right, when we squared when we squared y minus y hat, that caused us to penalize minor errors very to not a very high degree. And so we, in our practice, in our demos, we'll also try to not square and see how things go. Also, okay, now finally, this like a neuron is actually f wx plus b, and in the next lecture we will see what this f function is. Next, w equal to 2 and b equal to 0 are ideal values we assumed. However, for a single training example for an input w, I'm sorry, for an input for an input one second. For an input 4, if 8 is the only ideal answer, then you could also find that w equal to 1 and b equal to 4 is also right answer, and w equal to 0 and b equal to 8 would also be an ideal solution. So therefore, to generalize better, you would like to have multiple um, training examples. Okay. Um, and then, so instead of only giving x equal to 4 and y equal to 8, you just give x equal to 3 and y equal to 6, and it has to optimize for each of these simultaneously. And you'll find that our model is generally better. So when you give it x equal to 5, it'll predict, y equal to 10. Because if let me write everything down. It might be easier to follow that. X is equal to 4, w is equal to 2, wx comes out to be 8. However, y, as we know, y hat, right, should be 8. Let's y hat. How do I put a hat here? It's okay. I'm not sure how to put a hat on Desmos, so just assume y hat. That's y hat, whatever. So wx should be 8. That's the only objective. Then what you could also have is, because there's this variable b could have moved to the value of 4, and w could have moved to the value of 1, and we'd still get the same right answer. And so you may be like, okay, fine, what's the problem in that? As long as you're getting the right answer, right? The problem in that is that if x was 5 instead, 5, then you would get a wrong answer. You get 9. Instead, you're supposed to get 10, right? Because we're trying to find the generalized, like we're trying to train a neuron to become y equal to 2x. And that objective fails here. Okay. Then it's very, very similarly as we have done for w. In practice, we also vary b simultaneously. And so again, it's a simple derivative compared to, like, yeah, right? What you study in school is much more difficult. So delta y by delta b is going to be delta wx plus b. You assume wx is a constant, and so you get 1 uh, as the derivative of y with respect to b. But L with respect to y itself is a derivative. Therefore, the entire thing comes to be 2y minus y hat into 1, because dl by dy is 2 into y minus y hat. And you just multiply that 1 by 1. That is because of chain rule. Okay. All our future work will deal with training. And now let's look at how do we want to code this. Okay, all right. So let's first start by defining a neuron. Give me 1 second. Okay. Okay. So single. So and also the by the way, the process of moving towards the ideal value of W and B by calculating the gradients or like the derivatives, that's called gradient descent because you're moving down a gradient to reduce your loss with respect to each variable that might change. It's very intuitively uh, obvious, right? If you're trying to minimize something, you see what it's like, how much it depends on another variable. That's sort of what derivatives do. Okay, let's look at a single neuron. Import random. We want to start with a random value for W and B. And also W is called weight and B is called bias. And we'll do some plotting later. Okay, we can do that later. I will set random.seed as 0. What that does is it makes sure that all of us have the same values. Like when we generate random numbers, W is equal to random dot uniform, which uniformly chooses a value between say 1 and 10 short. And B is going to be random dot you could also do randint, which produces a random integer from 1 to like 1000 and divided by 100 to get a number between 1 and 10, another valid method. And um, and then what we're going to do is y is equal to w. Okay, we need to define x, right? X is equal to 4. Let's do a single example first. And we'll see how we won't get the optimal values for w for b and w. And then we'll move to having multiple training examples. Wx plus p. Uh, oops, yeah, we need a w into x. Also, we will set y hat as 8. Okay, I think that's it. We have a neuron here. Print. So let's run this. Okay, we got a random value for w, b, y is very off, and y hat should be 8. Okay, now we're going to do backpropagation and training. Um, let's calculate our loss first. L equal to y minus y hat, you square that. This is how you square in Python. Let's try out without squaring. So this becomes, let's print out the loss, which is L. Let's see what that is. It's a huge loss. Okay, we're really, really off. Now we will calculate our gradients, which is going to be fairly complicated. Let's look back into our notes and see how things work. Um, let's first calculate dl by dy because let me show you all the equations once more, right? I think it might be a little bit. Y is wx plus b and L is y minus y not square. So dl by dy is 2y minus y hat. Okay. Dl by dy is 2y minus y hat. Okay. So dl dy is 2 um, y minus y. In case you're wondering, we only calculate our gradients with respect to w and b, but not x because x is sort of an user given input, right? So we cannot change like what input we give to our function. We want to change parameters of the function, things that define what a function is out of all the possible functions that could be made. And therefore, we'll only change w and b because y is going to be an output of the function as well. So dl by dy is 2y minus y hat. Okay. And then uh, dy by dw is going to be, what is it? It's going to be x, right? Yeah, dy by dw is x. Okay. Then dy by uh, we can't put a slash sign in variables in Python. It'll actually just divide them. Dy by db is going to be 1. That's fine, it's 1. Now let's find dl by dw is going to be dl by dy into dy by dw, chain rule. dl d, dl dy into dy dw, and then very similarly dl db is dl dy into dy db. These two will cancel out. Perfect. Let's print that out. Uh, yeah. So these are gradients, very difficult to interpret what they mean. Let's move on. Okay, now we're gonna do a weight date. We're gonna follow this. Weight new is weight old minus alpha dl by dw. Okay, alpha is 0.01. Then w is going to be w old. In Python, we don't really need to define those two separately because the new w is going to be an old w automatically. Is going to be like this w will be an old w and then it will store it in the new w. Alpha into dl by dw. I don't. It's very easy to make mistakes here. And then b e p. Okay. Now let's print the new everything. Okay, y is 42.2. Wait, what? Okay, we did not recalculate y. Y is wx plus p. Let's recalculate. Making this a mistake. And y hat is actually 7.3 now. Interesting. That's interesting. Why is this happening? Let me debug this. Pretty simple error. So we keep moving towards the wrong direction because we did not recalculate all these gradients. So if we recalculate the gradients and then we run this, then we move back in direction. Okay, let's recalculate the gradients. On this, we're moving towards the right direction. We're getting closer and closer to 8. You want to monitor y. Closer. Nice. Very nice. Now we're getting closer to y, right? So let's just automate this with a loop. Um, let's run this 20 times. Um, we calculate gradients like this. And then we run reset alpha. We recalculate all this. Wait, we would. Interesting. I made another error. We'd have to recalculate loss as well. It's not only, yeah, we can't only run this. We have to recalculate that loss again. So that was working. Why was I working? We probably we don't necessarily need to recalculate. loss in this very specific situation. In all our TensorFlow training runs, we will have to calculate loss, which is why I got a little confused. But we are only looking in weight updates at how loss is changing. It's still useful to monitor loss to just see how well our model has been training. So we're going to monitor loss as well. So we calculate y. Um, Wait, let's do this. What am I? We will first do something called a forward pass. Y equal to wx plus b. Forward. This is typically how code is written, and for good reason. Then we calculate the loss. Then we calculate gradients. In TensorFlow, your gradients would be tied to you calculating loss. And then we're going to do weight updates. And after that, we're done. We let's also monitor our loss. So L, this is called splicing, by the way, in Python, where if you put an F before, no, so these are called F strings, and then if you put F before the string starts, and then you use these curly brackets, you can just put variables in your print. Okay, let's monitor this. Loss is power minus 6. WB are unpredictable, but see Y is very close to the right answer. And even though W and B do not have their ideal values, just because there's only one training example, we get this. And very interestingly, if we rerun this code, we'll get, and if we change our C, we'll get different W and B values. So now let's implement having multiple training examples. So our model is a little bit more useful because, and why it's not really useful, let me just demonstrate. Wx, W5 plus B. Why do I keep making 8.54? It should, I want this to be a y equal to 2x model. Uh, so let's implement multiple training examples. X is now going to be a list. I'll give 3, 4, 5. Y would be, give me 1 second. Actually, you know what? Let me show you one thing. Very interesting thing before we go into that. Losses list. Okay, and let's keep appending our and loss list. Sorry, what am I doing? Loss list dot append, and we append our current loss. And now let's just plot and see how the loss is dropping. Mhm. Import math dot py dot dot plot loss list. Oh yeah, right. We have to let's rerun everything. Yeah, interesting. Loss is dropping. Pretty cool, right? We sort of trained our own model that had random values and is now. And if you just do this on scale, you get. I mean, you don't exactly. You get really good models. Like in tomorrow's lecture, we're gonna build a model that's gonna read handwritten medical handwritten digits. Y hat is equal to uh, so y hat is gonna be 2 into 3, will be 6. 4 into 2, 8. 5 into 2, 10. Okay. Let's reinitialize W random dot. Now let's do the other method I told you about. Random from 1 to 1000 divided by 100. Good thing here is that you don't get 1.016666 like something like that, which is okay, just not very pretty well printed. There are other ways in which you can stop long things from getting printed as well. This will only prevent it from the first step anyway. It's not a very good way. Uh, y is equal to wx plus b. Will this work? Oh, it does not work because this is a list and you can't multiply a list with a number. So the y would itself be a list. And now we're going to do a little bit like challenging Python, something that we've not done yet. Um, let's look at this. Uh, y, okay, w small x into small x plus e for x in x. And in case you don't know how this works, it takes the first element of x, puts it in x within within these two brackets, and then it's like a loop. It's like a inline one line loop. I think that's what you call them. And then this x goes here, w into x plus b, and you get y. Excellent. Nice. Let's do our like this typical printing that we always do. That we've been doing. 345, 4.1, 9.41, and yeah, these values of y are really off, but that's what we're gonna train to improve. Okay. Now, how do we? What's our next step? When you first step is you make your model. This, I mean, a single neuron model. Okay. Now let's calculate loss. Till now, we used. I called it mean squared error, but it was just a squared error. And mean square error is a very popular error algorithm to find the error. There are many other error algorithms. We're going to look at some of them. This one is used a lot in image and we're going to use it tomorrow in it's used in image generation. It's used in a bunch of other things. We will look at examples. We'll study this later in good detail. So mean square error is going to be uh, you're going to find the square error between this y and this y hat, this y and this y hat, this y and this y hat, and you'll average them all. So let's calculate the square errors and then I'll average them. First, let's only calculate the square errors. So it's going to be again a little complicated. Y minus y underscore hat square for zip. Um, don't be scared. I'll explain what I'm doing here. Or sorry, y just uh, y comma y underscore hat in zip. Yeah. So what this does is what zip. Wait, don't open one second. One second. Yeah. Okay. So what zip does is it takes the first element of y and my goodness. Yeah. Takes the first element of y, this list, and puts it in y, the small l y, takes the first element of this capital Y hat, puts it in small y hat, and then you calculate y minus y hat square, and you put each of those results in a list. Print. Okay, you got the square error for square errors for each of them. Now we just need to mean them. So you do a sum for all of these for this whole list. That's a function in Python. And then you get the length of x because that's going to be same as the length of y hat, y, and l. Or you could just make this y, whatever, right? All of them have the same length. And this is going to be the mean square error. Hopefully, I've not made a mistake here. Okay. Now we're gonna do. Now let's do a training code. Loss list is an empty list for I in range. Now let's train this for 50,000 samples. 50,000 samples. Let's start with 5,000 samples. And then y is going to be w into small x plus b for x. X Okay, this is what we call a forward pass, and it's called a forward pass because you're passing your data through the model. And now the next step is we calculate our loss. We just copy this code, put it here. Now backward. Great. Yeah. This is going to be much more annoying. It's going to be much more challenging. Okay. We're going to have to calculate the gradients for each example separately. And then we will do a weight update to our model for each individual example. And then I will teach you something new. Okay. So we know that dl by dy, let's just copy a little bit of the old code. Yeah. But dy is 2 into y hat. Now we just need, because these are lists, we need to replace this with y and y underscore hat. We'll do the same thing as we always do. For y comma y underscore hat in zip y comma y underscore hat. Um, and so each of y goes to this, each of capital Y goes to small, each training example, and then you calculate the error for that training example. You don't calculate the error, you calculate the gradient, uh, and you put that in a list for each training example. And because X is a list and DL by DW automatically becomes a list, we don't really need to do anything here. This will become it will be one for each example. So this list is going to be the length of the amount of examples we have, but for each of them, it's just one. So there's going to be 1 into the length of y or anything else. All of them have the same length. Again, here we're going to replace this with small alphabets because we're going to count it for each of them. Okay, dy dw. For dl underscore dy, comma dy underscore dw in zip dl underscore dy, comma dy underscore dw. I hope this is right. Okay. Yep. Okay. And so we do the same thing here. Really simple. You're moving for dl underscore dy, come dy underscore dz. And so you might want to write the next section after. Well, let me just write the section. Underscore dy, comma d. Perfect. Now we will do a a weight update for each individual example individually. Now that you've seen how this code has been going, you might want to try that on your own. So go ahead and try that. Uh, I will proceed to code it on my own. Yeah. Now that you're done, if you have coded that, I will show you how to do it. Uh, what we want to do is for I in range, the length of, I'm writing this for the first time. I'm not written sample code for this. For I in range length of y, for each example, you want to do a gradient update. And so the new w is going to be the old w minus alpha into um, the gradient. And so the gradient, from the list of gradients for the w, you pick out the ith element. So for the zeroth example, you pick out the zeroth gradient and you do a weight update. And then when y become when for the first example I becomes 1, you pick out the first gradient and you do the weight update. Similarly for b, b minus alpha into, and I hope you understand why it's minus, right? If the gradient increases as you move towards x, sorry, gradient increases as you move towards x, you want to move in the backward direction, you want to go down. dl underscore db and I. If the loss increase, yeah, if the gradient is positive, so not gradient increases, I'm sorry. When the gradient is positive in the direction of x, you want to move opposite to the direction of, for example, the gradient positive would be upwards, right? Um, Now we can do this, and now let's print out. I think everything is good. Okay, let's print everything out. Okay, but one thing we want to do is, just because there's going to be 5,000 examples, we can have a 5,000 print statement. That's a little bit too much. What I would like to do is, when, if I, oh, oops, we used I twice. Oops, that could have been a problem. Let's call this ix, right? If um, it wouldn't have been a problem, but whatever, right? If I um, percentage, let's make let's replace this with a variable. So what this is saying is, you have 5,000 iterations, you divide it by 20, so that's 250. If I is divisible by 250, percentage means like when you divide, what's the remainder? If that remainder is zero, that means it's divisible. Then you will print. So regardless of how much ever I increase my iterations, as long as it's divisible by 20, then it's also going to be divisible by, it was divided by 20, and so you're going to be fine. Print the typical things that we print. Let's get that statement. Loss and everything else. Also, we want to store all the losses in a list, right? So let's get these two statements. Mm, in case you may be wondering why, that's, yeah, why we did not calculate loss separately for each example. The thing is, it doesn't matter. Uh, like mathematically, your updates will not really be affected by if loss is just something you want to monitor, right? Like, are we going towards the right direction, the wrong direction? Is our model learning? How well is it learning? So you don't want to monitor too many things. For now, again, we're going to see something, how things get more interesting later. Um, and already W is getting very close to 2. I am so stupid. I created a very complicated print logic for printing, and then it just not print anything. Yeah, let's redo this. Okay, what you see is W is really, really close to 2. P is 2 into 10 power minus 9. And so we've reached what we would consider something to be like to be a pretty ideal value. Let's run this for 50,000 iterations and run everything once more. Oh, did it run? Oh, oh yeah, it did. Okay, nice. So now let's see if it generalizes. Let's see if y, sorry, w into 5 plus b gives us 10. Perfect. Great. We've done exactly what we wanted to. Uh, One thing we want to do is let's try to do is to plot the loss. Let's see how that has fallen. Plt.plot loss list. Yeah, it's not because most of the loss dropped very initially, so it's not that clearly visible. Maybe if we do a log scale, we'd be able to see things better, but it doesn't matter. Is there anything else we could do? I think that's it. We have successfully trained one neuron to model multiplying multiplying a number by two. And this, believe it or not, this was probably one of the like like a very conceptually difficult class. It was a lot of gradients, a lot of math. Um, it's not like math will stop, but we covered a lot of the basic concepts. We When we scale up to bigger models, we will have a bunch you know like one of the latest models by Meta has 2 trillion such random values that they encode. People estimate that GPT 4.5 has, I think, 12 trillion to 20 trillion such parameters. And now we just had two. And so the entirety of AI is going to have a lot of the same concepts. We're going to introduce a few new things, um, but scaling is the problem that becomes very, very difficult to challenge as we move further. Okay, thanks a lot. Um, I'll be to see you in the next lecture. Have a great day. I forgot to mention one thing. Here we've done um, our gradient update for each example individually, right? In practice, it's actually much better to do the gradient update for the entire batch all at once. Because, like, let's say sort of uh, x bar 4x is generate a random function plus 3x minus 3x cube plus 7x minus 7x. Okay. Now, let's say when we were trying to, uh, let's say the actual gradient lies over here. Over one training example, like the direction of which gradient is the points to the right direction for all parameters for the entire model might not necessarily be right for that particular example when you have a bunch of examples. So what's noticed observed is that when you average the gradients across an entire batch, then you're able to estimate the right value of the gradient for the entire model in a much better way than for each particular example. And this is what we will be implementing now and in all future um, coding endeavors. So let's do an averaged update. All the changes. Um, W is going to be, let's comment this out. Control and slash, by the way. So W is equal to W minus alpha into, now let's do an average of DL by DL DW. Sum DL underscore DW divided by len DL underscore DW. Okay. And then we do the same thing for E. E is equal to B minus alpha into uh, sum DL dB divided by DL dB. Sorry, len DL dB. What am I writing? Hmm, let me just check if this is right. Yes. Okay. And so now this will perform a little bit better, train a little bit faster. You can explore that on your own. Additionally, I told you about us not using mean square error as well, right? So why don't you try to remove this square and see how the model performs? Replace it with a cube and see how the model performs. Um, but also you want to keep in mind that if you remove this square, then you want to remove this too, right? Because the gradient as well. You want to calculate the derivative properly. And you only want to remove this because dydw and dydb does not change. Only dldy will change, and you can sort of write it out on paper and think about why that is. And if you replace this with a cube, then this will become 3 into y minus y hat square. So try it out and see how things go for you. Have fun. See you.